to this lesson. I'm teacher Agnes, and today we are going to be discussing about atmospheric pressure. So in the previous lessons, we learned that for pressure to be exerted, then a force must be applied on a particular area. Now in the atmosphere, we have air, and that air has its own weight. So the pressure that is exerted on the surface of the earth due to the weight of the air column is what we refer to as atmospheric pressure. So let us assume this is our earth, okay? So above the earth, we have the atmosphere. So this is the atmosphere. In the atmosphere, we have air, okay? We have air in the atmosphere. Now this air has its own weight, and the weight of the air is exerting a pressure on the surface of the earth. So the pressure exerted on the surface of the earth due to the weight of the air column above it is what we refer to as atmospheric pressure. So atmospheric pressure is a phenomenon that exists on a daily basis, and we are going to do an experiment to demonstrate that there is atmospheric pressure in the atmosphere. In this experiment, we are going to prove that there is atmospheric pressure in the atmosphere around us. In the presence of air, there is always air pressure, which is the other name for atmospheric pressure. In this experiment, we are going to use a basin, cold water, hot water, and then a bottle. The first step that we are going to do is to put hot water in this bottle. And the reason why we are going to put hot water is so that the hot water can produce steam. So if steam is produced, then now since I'm going to have the water partially in the bottle, the rest of the space is going to be filled by steam. That means that if I cool the bottle, then the steam is going to condense back into water. And when that happens, a vacuum is going to be created. Now, if a vacuum is created, that means there is no air in that vacuum. And if there is no air, then there is no air pressure. So then we will observe what happens. So please pay attention, remember the steps. So we are going to start by putting hot water in this bottle without filling it. Okay, so like you can see, the steam being produced, and then we are going to have this tightly closed so that no air can come in. So we have the water in the bottle, and then the rest of the space is occupied by steam. So if we cool this bottle, what will happen to the steam? The steam will change back into water, and the space that is currently occupied by the steam will be a vacuum. So we will pour cold water on the bottle. So I hope you can see what is happening to the bottle. Okay, the bottle is getting crushed inwards. Okay, if we give it more time, it's going to lose its initial shape into a deformed bottle. So what is the science behind this, and how is atmospheric pressure responsible for this? So like we have stated, in the space without the water head steam, after cooling, the steam is converted back into the water. Now the space that was occupied by the steam is now empty. It's now a vacuum, which means it doesn't have air. And in the absence of air, there cannot be atmospheric pressure. There cannot be air pressure. Now outside the bottle, there is air, and there is atmospheric pressure. Now since the pressure outside the bottle is more than the pressure inside the bottle, then the pressure outside pushes the bottle inwards, and that is why the bottle is able to crash. So notice that in this case, there is a pressure difference. The atmospheric pressure from outside the bottle is more than the pressure inside the bottle, and that is why the atmospheric pressure is pushing the bottle inwards. So as we live on the surface of the earth, there is always atmospheric pressure that is acting on us. We may not feel it, but this is proof that there is atmospheric pressure in the atmosphere. So I hope you have understood the concept, and now we are going to continue with our lesson. Now we have seen that in the atmosphere we have atmospheric pressure, and the only reason why it exists is due to the air that is in the atmosphere. And like we have said, the air in the atmosphere has weight, and when weight acts on a particular area, then pressure is created. So we conclude that atmospheric pressure is the pressure exerted on the surface of the earth due to the weight of the air column in the atmosphere. Now the atmospheric pressure acts in all directions. It can act upwards, it can act sideways, it can act downwards. So we are used to pressure acting in a downward direction. If you are below water in a swimming pool, then the water will be exerting pressure on you in a downward direction. If I place this book on my palm, it will be exerting pressure on my palm in a downward direction. But atmospheric pressure acts in all directions. And we are going to do another experiment to demonstrate that atmospheric pressure can act in all directions. We are going to do an experiment to demonstrate that atmospheric pressure acts in all directions. Unlike other, when other objects exert pressure on surfaces, the pressure acts in a downward direction. This basin is exerting pressure on the table, but in the downward direction. If you are swimming in a swimming pool and you are diving at the bottom of the swimming pool, the water will exert pressure on you, but in a downward direction. So now to demonstrate that atmospheric pressure can either act sideways or in upward direction, we are going to do an experiment, and we are going to use a tumbler here, cold water, this basin, and a piece of paper. Now we are going to fill the tumbler with water to the brim. So you must fill it to the brim and ensure there is no space that is left without the water. So we are going to cover this tumbler with a piece of paper, and at the top make sure that the water soaks in the paper, and then slowly we are going to turn it upside down. So after placing it in the right place, we are going to turn it upside down. Now after turning it upside down, I will release my palm from the bottom, and then we observe what happens. So like you can see, the piece of paper has been held in place, and the reason why it is held in place is because we have atmospheric pressure acting in upward direction on the paper, and the atmospheric pressure is even more than the pressure of the water, and that is why the paper had been held in place. So that is proof to show that atmospheric pressure can act in the upward direction, which means that atmospheric pressure can act in all directions. Now to demonstrate that atmospheric pressure also acts sideways, we are going to refer to the bottle that we deformed in the previous experiment. Remember it? So like you can see, the deformation has actually happened in the sideways direction, inwards. And that means that the atmospheric pressure is acting on the sides of the bottles from the sides, which is another proof that atmospheric pressure can act in any direction. Now, if we open this bottle, we are going to give room for air to get in. Remember that atmospheric pressure is caused by air. Where there's air, there's atmospheric pressure. So if air goes into the bottle, what is going to happen to the shape of the bottle? Let's find out what will happen. So if we open, okay, like you can see, the bottle is trying to regain its original shape. Why is that the case? Now, inside the bottle, air has gone in. And if air has gone in, then now there's atmospheric pressure inside, which is pushing now the bottle outside. So in this case, it's like air has gone pressure inside, then now, and the one that is outside have balanced. Okay, now there's atmospheric pressure, the pressure inside, and that is why is pushing now no crashing or deformation anymore. So this is proof that atmospheric pressure can also act sideways, which means that atmospheric pressure acts in any direction. So having now learned that, we are going to proceed with the lesson. Now in this part of the lesson, we are going to discuss how does a drinking straw work. I know you must be there asking yourself, what does this have to do with physics? Well, science is there in everything. Now, a fun fact, the first drinking straw was invented by a person called Marvin Stone in 1888. Well, it is said that there were other people who had invented drinking straws before, but Marvin Stone was the first person to patent a drinking straw. So this tells you that whenever you come up with an idea, before someone steals it, you need to patent it so that it is accredited to you. Now, why did Marvin Stone invent a drinking straw? It is because one day he was taking a cold juice, and while taking the juice, he took it together with a piece of grass that was in the juice. So he invented a straw so that where in case there are any big particles in a drink that should not be there, as it drinks to the straw is supposed to prevent the pieces from passing, to you, because if you use a straw, then such big objects cannot pass through the straw. But how does it work in terms of physics? How is it that we are able to drink using a straw? Now, what I have heard about drinking straws in Kenya is that they were introduced for health purposes, okay? Long time ago, people used to consume sodas with the bottles, but the same bottles are recycled, and it was argued that those bottles could be contaminated. So to prevent that, drinking straws were introduced in Kenya. Now, when you are using a drinking straw, I want you to imagine the first thing that you do. You put the drinking straw in your drink, and then you suck the drink, right? Yes. So like you can see in this diagram, we have a glass here that has a drink. Then we have this person here who is drinking from the straw. So the first thing to do is to suck. What happens is that inside the straw, there is air. And we say where there is air, there is atmospheric pressure. So if you suck, the air will be pulled from the straw into your mouth, and there will be left with no air inside the straw. If there is no air, then it means there is no atmospheric pressure inside the straw. There is a vacuum. Okay? Now, since on the surface of the drink, there is atmospheric pressure pushing the drink inwards, the atmospheric pressure is going to push the drink inwards, and since the drink is looking for an escape, it will go up the straw because a vacuum has been created. So pressure difference again. So when you suck from a drinking straw, you suck out the air, which creates a vacuum inside the straw, and that means that there is less pressure inside the straw. Now the greater atmospheric pressure acting on the surface of the drink pushes the drink upward to you through the straw. And that is how a drinking straw works. Okay? Now what else works on the same principle? Sometimes you go to the hospital and you find that a doctor is pulling drug from a bottle with a syringe. So what happens? When a syringe is pulled, that region inside the syringe has no air. There's less pressure inside the syringe. So the atmospheric pressure acting on the surface of the drug is able to push the drug into the syringe. Now when it comes to the doctor injecting the medicine in your veins, they now push the syringe. And when they do that, they create more pressure inside the syringe, which is more than the pressure in your blood. And that's how they are able to push the medicine into your blood. So they create more pressure by pushing the syringe, which is greater than the pressure of your blood. And that's how they're able to put the medicine into your blood system. Now the opposite is true. If the doctor is pulling blood from you, they pull the syringe, creating a vacuum inside the syringe, which has low pressure. So the more blood pressure which is running in your veins pushes the blood into the syringe. Hear the difference? So when the doctor is pulling blood from your veins, they pull the syringe, creating a vacuum. Okay? That vacuum has low pressure that is lower than the blood pressure, than the pressure due to the flow of your blood. So the pressure coming from the flow of the blood pushes the blood into the syringe. Did you know that those illustrations work on the principles of physics? Now, here is a question for you. Why is it that when someone who lives in like a coastal region, when they visit like the Mount Kenya region, they are likely to bleed? Okay? So when that happens, let me show you an illustration. So here we have someone at the coast, then here we have someone in Mount Kenya region. So let us take this level to be the end of our atmosphere. This is how far the atmosphere is. So the person in coast has all this air above them. The person in Mount Kenya region has this air above them. We said atmospheric pressure is the pressure due to the weight of the air column above the Earth's surface. So the air above the person in coast is more than the air above the person in Mount Kenya region. Okay? So if the air is more here, then that means that the atmospheric pressure is also more. So remember, we cannot keep on bleeding out because the atmospheric pressure is actually responsible for ensuring that our blood remains within our bodies, because the atmospheric pressure is more than the pressure due to the flow of the blood. If the pressure due to the flow of the blood is more, then our blood would be flowing out in the openings that we have. So notice that here the atmospheric pressure is more, but here the atmospheric pressure is less, meaning that there are some people who are affected when they go to regions with high altitudes, because the atmospheric pressure is now less than what the body is used to, and this atmospheric pressure is not able to contain the blood from within. So you find that when some people go to regions of high altitudes, the pressure due to the flow of their blood becomes more than the atmospheric pressure, and they are likely to suffer from nose bleeding. Okay? Now, let me ask another question, because for us to understand the concept of atmospheric pressure, we have to look at all these scenarios. Now, knowing what you know now about atmospheric pressure in comparison to the amount of air above us, why is it that if you carry a pen to the aeroplane, it is likely to pour its ink out? Okay? So remember, if this is the surface and this is where the plane is flying at, again, the atmospheric pressure above the plane is less. And if it is less, then the atmospheric pressure will not be able to contain the ink in the pen inside the tube. If the atmospheric pressure is less, the ink will just flow out. Okay, the ink will flow out and just flow out of the pen due to the reason that the atmospheric pressure is now less and cannot contain the ink inside the pen. Now there are so many scenarios that happen due to atmospheric pressure, and I challenge you to try and think of something that you think exists or happens due to atmospheric pressure that you have never thought about before. Now let us find out. So we are going to do one question that is going to need the knowledge of atmospheric pressure. Now in this question, we have a piece of stone that is 20 meters below the surface of the water. And like you can see, the container in which it is put is an open container. Now, as long as that container is open, then it means we have atmospheric pressure acting at the top here. So when we look at which types of pressure are acting on the stone, then we have atmospheric pressure, and then we also have the pressure due to the height of the water. Okay? Now, since we want the total pressure, and we have already been told in the question that the atmospheric pressure is equal to 100,000 pascals, we will first calculate the pressure due to the height of the water. So pressure due to the height of the water is given by, water is a liquid, and we calculate pressure due to a liquid using the formula height times density times gravitational force. Ensure that the height and the density are in the SI units. The height is given in meters and the density is given in kilogram per meters cubed. So we are good to go. We don't need to convert anything. So the height is 20, the density is 1000, and the gravitational force on Earth is 10. So if we multiply this, we have 20 times 1000 times 10, which is equal to 200,000 pascals. Now, having obtained the pressure due to the height of the water, we are now going to add the atmospheric pressure to obtain the total pressure acting on the stone. So, in this case, to obtain the total pressure, we will have 100,000 plus 200,000. When you add the two, you will be able to obtain 300,000 pascals. So it is important to note that as long as the container is open, the atmospheric pressure is acting. Example 2, we are going to work out this question. Like you can see, we have a container. This container has two liquids. It has paraffin, then it has water. We all know that paraffin does not mix with water, and paraffin settles at the top. Why? Because it has a lesser density than water. Now, this container is open at the top, which means that the two liquids are experiencing atmospheric pressure, which is acting in the downward direction. So in the question, we have been given the value of the atmospheric pressure, which is 105,000 pascals. Now, I know you could be asking yourself, why is this value of atmospheric pressure different from the one that you have used in the previous question? Now, remember, atmospheric pressure changes with altitude. So the atmospheric pressure in the coast is different from the atmospheric pressure in Mount Kenya. The one at the coast is more, because the height of the air column above the Earth's surface is bigger at the coast. Now, the density of paraffin is given as 800 kilograms, and the density of water is 1000 kilograms per meters cubed. The density of paraffin is also 800 kilograms per meters cubed. The value of the gravitational force on Earth is 10 newtons per kilogram, and now we are required to calculate the pressure at the bottom of this container. So this is the bottom of the container. So it is important to ask yourself, the pressure at the bottom is as a result of what? So in this case, we have three things contributing to the total pressure. One, we have the atmospheric pressure. Two, we have the pressure due to the height of the paraffin. And three, we have the pressure due to the height of the water. So we need to get each one of the three and then we add them together to get the total pressure at the bottom. Now, since the atmospheric pressure is given, we will not be calculating it, but we need to calculate the pressure due to the height of the paraffin. Remember that paraffin is a liquid, and pressure in liquids is given by height times density times gravitational force. So, the height of paraffin is 60 centimeters. Can we use the 60 centimeters in the equation? We will need to convert 60 centimeters into meters so that we can be able to cancel out the units. So every time you are substituting values in this formula, ensure that they are in the SI units. So 60 centimeters, how do we convert centimeters to meters? We divide by 100. Refer to our lesson about length because we learned how to convert this. So height will be 60 divided by 100 to convert it to meters. Now the density of paraffin is 800 and the gravitational force is 10. So we can call this pressure 1. This is the pressure due to the height of paraffin. So to work this out, we cancel out the two zeros. So we have 60 times 8, which is 480, times 10, which is 4,800 pascals. Okay? That is the pressure due to the height of the paraffin. Now we are going to calculate the pressure due to the height of the water. So we can call that our pressure 2, which is still given by H rho G because water is a liquid and pressure due to a liquid is calculated by multiplying the height, the density, times the gravitational force. Now make sure you are not confusing the figures. Now since in this case we are dealing with water, we must use the height of water and the density of water. Don't find yourself using the height of water and the density of paraffin. That will not give you the accurate value. So since we are dealing with water, use the height of water and then use the density of water. So the height of water is 1.5 times the density of water is 1,000 times the gravitational force, which is 10. So if we multiply this, we will get 15,000 pascals. So now we have the pressure due to the height of the water and pressure due to the height of paraffin. Then we know that atmospheric pressure is equal to 105,000 pascals. So now we can get the total pressure. So the total pressure will be equal to the sum of the three. So now we have 105,000 plus 4,800 plus 15,000. Now adding this, we will get 124,800 pascals. So this is the total amount of pressure that is acting at the bottom of the container. So let us do one more example. Now in this question, we have a diver who is 10 meters below the surface of the ocean. So divers are those people that swim deep in the oceans. Now given that the density of seawater is 1,030 kilogram per meters cubed, and the atmospheric pressure is 102,000 pascals, calculate the total pressure acting on the diver. Now you might be asking yourself, why is the seawater having a different density now. Remember, seawater is salty, so it's basically a mixture of water and other, elements. And as a result, the density of seawater is higher than the density of pure water, which is 1,000 kilograms per meters cubed. Now, in this question, we have two types of pressure acting on the diver. One, we have the atmospheric pressure, and two, we have pressure due to the height of the water above the diver. So we are going to calculate pressure due to the water, which is given by height times density times gravitational force. Now this is equal to the height of water above the diver is 10 meters times the density of seawater, which is 1,030, times the gravitational force, which is 10. So if you multiply this, you get 103,000 pascals. So this is the pressure due to the height of the water. But remember, above the water, because if this is the ocean and we have water here and the diver is below here, we have pressure due to the atmosphere and we have pressure due to the height of the water. So to get the total pressure will be equal to the atmospheric pressure, which is 102,000 pascals, plus the pressure due to the height of the water, which is 103 pascals, and this will be equal to 205,000 pascals. So this is a lot of pressure acting on a person, and that is why when divers dive deep in the ocean, they wear protective gear. And that also tells you why nobody can really survive at the deep, the bottom of the deep waters without very protective gears, because it would be dangerous and the pressure would actually crush you and kill you. And that is also why some species in the ocean do not survive deep at the bottom of the ocean. They are those that have what it takes to survive at the bottom of the ocean. Now, having learned this, we have explored a lot to do with atmospheric pressure. The lesson has been very engaging and I hope that you have enjoyed. So now I'm going to give you some exercise questions that you are going to use to practice whether you have understood what you have learned in this lesson. Now, students, you are going to attempt these two questions. Number one, explain how a fountain pen is filled up with ink. Number two, given that, so we have this diagram here, we have a stone at the bottom, the height of the water is 90 centimeters. Now, given that the atmospheric pressure is 100,000 pascals and the density of water is 1,000 kilograms per meters cubed, then calculate the total pressure acting on the stone. So I hope you have learned a lot in this lesson. It was quite an enjoyable lesson, and thank you for your patience. See you in the next lesson.